spent the last several lectures learning about these equations right here. These equations that help us to calculate the velocity of a particle or the acceleration of a particle using a moving reference frame. And so if we know the velocity and acceleration of the origin of that reference frame, how the particle moves relative to that reference frame, and then all of these parameters having to do with the rotation and angular acceleration of the reference frame, these equations help us to work out what the total velocity and total acceleration are. So in this class, we'll talk about how this applies to us living on planet Earth and the motions that we see on our moving reference frame. Living on Earth, what we see and measure are usually these relative velocity and relative acceleration. We see how we move relative to the surface of the Earth. But in a broader scheme, we're on a moving reference frame, planet Earth, and so let's see what these equations can tell us about that. So, now everything moves, and so it's hard to say where we can establish a reference frame, but for the purpose of this class, let's just consider a couple things. The Sun is part of a galaxy, and the Milky Way galaxy, and so if we knew where the center of that galaxy was, we could say that the Sun is tracing out a circular path through that galaxy. I guess that we don't know that it's exactly circular, but it's actually roughly circular, the path that the Sun's taking. And then relative to the Sun, we all know that the Earth is moving at some speed relative to the Sun, such that it makes one revolution every year, right? And then us sitting on the Earth here, the Earth itself is actually also spinning. So let's look at each of these effects one at a time and see how large they might be and when we might account for them. So first of all, the Sun relative to the galaxy. So this picture shows where our Sun is relative to the center of the Milky Way galaxy. And astronomers have calculated that that distance between the center of the galaxy and us, this distance right here, which we call rho sub s, that's 33,000 light years. And so as we travel around the Sun here, we're moving at about 180 miles per second. Amazing, right? I mean, we're screaming through space. And so if you do the math on that and you work out the acceleration, right, if we have a velocity and we know the arm, we know that our acceleration is just v squared over rho. And if you do all the conversions from light years, say, to miles per hour, this gives us an acceleration of less than 10 to the minus 7 g's, or 10 to the minus 7 times the acceleration we get due to gravity. So this is pretty much always negligible as far as we're concerned on Earth. We'd have to have a very, very sensitive instrument to even measure that, right, to even be able to pick that up. So it's not likely to affect us if we're sitting here on planet Earth. If we're planning the motion of a spacecraft from the Sun to the far reaches of the solar system, then we might account for this. But for most purposes, that's pretty negligible. So what about the Earth relative to the Sun? Well, this is an enlarged view, but the Sun, the Earth we know is the third planet out from the Sun. We're at a distance of 93 million miles from the center of the Sun. So that's our rho, our moment arm from the Earth to the Sun, from the Sun to the center of the Earth. And we're moving around in a circle, as we said earlier, so that we make one revolution per year. So if we do the math in this case, we get 0.06% of a g, or 0.0006 g's. So this is large enough that we might actually be able to measure that. with a very sensitive instrument, very delicate instrumentation. So in some cases you might actually be able to pick up and tell that this is happening. And so as we're sitting on the earth, if we're standing on this side, with our head towards the sun, versus standing on this side, so every day as the earth spins, we would measure a different weight by this amount. If you weigh yourself, if you weigh yourself at night, then you'll find yourself weighing just a little bit less, right? And that could be motivation to keep up your exercise routine. Okay, so anyway, that is our motion relative to the sun. Simple circular motion again. And things start to get really interesting when we start to look at how we're moving relative to the earth. And it also gets more complicated. So this picture shows the top half of the earth. So here's the equator. Madison, Wisconsin is sitting up. Let's see, that's at about, was it 42 or 46 degrees? I have it written down somewhere. Anyway, we're sitting up in a fair distance from the equator, sitting in Madison with our origin here. We might measure our position in XY coordinates. In this case, X would be east and Y would be north, right? And then Z would be straight up into the air is what we would measure. So we would measure a position relative to Madison, and we would define our position vector using that. So the Earth, though, is spinning on its axis, an axis roughly perpendicular to the equator, and it goes through about one revolution per day. Now, if you account for leap years and everything, maybe you can refine that a little bit. But anyway, if we take our angular velocity and we know the radius of the Earth, we know about how far we are from the center of rotation. Though notice our angle of longitude actually does matter, this angle lambda. If we have a lambda of 0, we'll be down here on the equator, we'll have the largest possible velocity when we take omega across r. In contrast, if we were on the pole, we don't get any relative velocity from this effect. So we have to account for the geometry and account for all of that to figure out how we're moving relative to the Earth. So if you work out the math, we get this equation that says our velocity ends up being 1520 feet per second. So that's greater than 1,000 miles per hour. So we're really screaming along on the surface of the Earth, just standing here, right? Really moving along. And again, that depends on the cosine of the angle lambda. So at the equator, that cosine goes to 1, and we get the full speed. Up at Madison, we get just a little bit less than that. And you can also work out the acceleration we get, the centripetal acceleration. And if we do that, if we work all of that out and we convert this, this actually works out to 0.35% of a g. So this is very readily measurable, and this has an important effect on various things. So it's something that we need to be aware of. A fun little fact, suppose you could buy gold in Madison, right? In Madison, gravity is a little bit less, right? Actually I'm telling you that backwards. On the equator, I guess we have the maximum acceleration that we can get, right? Due to this centripetal motion, which is wanting to basically throw us off the Earth and counter the effect of gravity. So if we could go to the equator and we could buy gold. And we could take the same scale that was used to sell us the gold and get the people in Madison, Wisconsin to use that scale to sell the gold, right? So if they ignored the calibration, they ignored this effect, we could make basically $3 per ounce buying and reselling gold. So not a huge amount compared to the cost of gold, but maybe enough that we need to worry about it. Another funny story along these lines, a friend of mine worked at a company where they would send parts off to a mass properties lab to have them measured. So the mass properties lab would measure the part, get the mass very accurately. They would also measure the moments of inertia, which we'll talk about later. And then they would print up a sticker that reported all of these values down to 6 decimal places. And then they would slap that sticker onto the part. I'll leave it to you to think for yourself, why is that funny, right? We would always joke, well, I wonder if they accounted for the ink on the sticker when they did their weight, right? Anyway, let's talk about one example here. So we'll switch over to these notes here. And let's imagine using these equations to find the equation of motion for a particle that's floating in the atmosphere. So again, these here, oops, it's not wanting to let me write. Let's try that one more time. So these here, this is a point on the surface of the Earth, somewhere like Madison, Wisconsin. So this is the motion of a point on the surface of the Earth. And if we're a particle, we might know the velocity and acceleration relative to the Earth. And we want to use that to find an equation of motion so we can calculate how these accelerations will cause a particle to move as it's floating in the atmosphere. So imagine we have some little particle here, and let's say it's a really light particle, so that if we were to look from in the z-axis, we would see that particle, and we'd see some buoyant force, and we'd see gravity pushing it down, and those two are canceling each other. So the sum of the forces on this is just the buoyancy minus gravity. Those are both in the z direction. And those cancel, so they're equal to 0. So there's no other forces acting in the plane. The particle's just floating freely. So we're neglecting drag or aerodynamic effects, only accounting for just the motion of the particle, or just the acceleration of the particle relative to the Earth. Okay, so if we do that, what we find, the sum of the forces is always equal to mass times acceleration. And if we go up into this equation up here, this is our position of our particle relative to the origin of the Earth. And if you recall, back in this picture here, we used the radius of the Earth, which is almost 4,000 miles, to figure out what our velocity is relative to the center of the Earth, right? So if we've done that, any radius we put here, if it's small relative to 4,000 miles, then this term's going to be negligible, because this term here is omega cos the radius of the Earth. So basically that tells us that we can neglect this term, and we also then end up neglecting that term and that term. And the acceleration here, this would be the rate of change of angular acceleration of the Earth. So the Earth doesn't change its rotation speed very quickly. It's had a steady rotation speed for thousands of years, so we can neglect that. So anyway, if we do that, the only term left in the acceleration is the acceleration of the origin of the coordinate system and our relative acceleration, and then this last term, which is called the Coriolis acceleration. So the sum of the forces is equal to mass times acceleration, and we could also add in here the mass times that 0.36 g's that we mentioned earlier, and that'd be roughly in the z direction, I guess we'd say. So that affects this buoyancy equation, but doesn't affect anything else. So we'll just say that cancels over there. And anyway, the sum of the forces then is equal to 0, which says that this term has to match this term, or the acceleration relative to the moving reference frame has to be canceled by the Coriolis acceleration that we get. So that lets us solve to say that the acceleration of our particle that we will observe from the Earth will be 2 omega cross v. So this acceleration only depends on the velocity, so it'll depend on how the particle is moving relative to the surface of the Earth. And this is the angular velocity of the Earth itself. So that will govern the acceleration that particle sees. So one really interesting application of this are hurricanes. So a hurricane is has a low pressure center. So we have hot air rising, which causes lower pressure near the center of the hurricane. And so any air around the hurricane wants to get drawn in, right? And so these particles in the hurricane have a velocity in towards the center that we'll call our VP relative to XYZ. Now what happens next depends on whether we're in the north hemisphere or the southern hemisphere. In the northern hemisphere, the angular velocity vector will be coming out of the page at us. So that vector coming out will so that's a vector coming out. I draw it this way so that by the right hand rule I could put my thumb up in the air and know which way the angular velocity is. So we can use this equation then to calculate which way the acceleration will be. What this says is if we have an angular velocity out, so we put our fingers vertical in the direction of that angular velocity. So from this view, you could see 4 fingers coming out and a thumb, and there's a hand. Very good artwork. And now we're going to curl those fingers towards the direction of velocity because we want omega crossed into v. So we curl that for this one here in this direction, and we get something, then we get our thumb pointing down this way, right? But the acceleration is the negative of that, so that tells us that AP has to be a vector this way. And interestingly now, if we go and we do the same thing here, we get our thumb pointing to the right, but then we put the negative sign in, and we get another AP relative to XYZ. And if we keep going around the circle, we find that the acceleration is always counterclockwise. So that tells us that the motion of the Earth, coupled only with this velocity, will cause the particles in this hurricane to rotate counterclockwise if it's in the northern hemisphere. So we can go ahead and we can actually check this calculation. People luckily have been able to take videos of hurricanes from space. So if we look at one of these, this is a video of a hurricane in 2018, Hurricane Florence, and notice the particles, which way are the particles moving? You can see the rotation. You can see even better here. The rotation is in a counterclockwise direction. Way out here on the extremes, the particles, maybe they're acting due to a different pressure. They seem like they might move a different way. But the center of the hurricane is rotating counterclockwise. And it's harder to find videos of the southern hemisphere. These aren't called hurricanes, they're just called tropical storms. But here's some videos. It's harder to pick out, for me to pick out locations in these videos, but notice these ones are rotating clockwise. All of these storms show a clockwise rotation. So you can see that in all of those. So, so interesting, in the southern hemisphere we can see that we get a clockwise rotation, or the opposite of what we calculate for the northern hemisphere. And again, this all comes about due to the Coriolis effect, or the fact that these particles are floating above the Earth, and they have an inward velocity, and the Coriolis acceleration causes them to spiral as they come in. Notice here you can see this is the northern hemisphere. There's Florida. You can see the east coast of the United States there. So, so that explains something about that. Sometimes you hear people say that you could use this same analysis to explain why toilets spin one way or the other, but actually you could debunk that. Toilets have quite a bit of a lateral component to the flow, so that the in-plane forces aren't negligible, and so usually the rotation of a toilet just depends on the design of the toilet, not on a Coriolis effect. Maybe the direction that a vortex goes as water leaves your bathtub could be affected by this as well. Okay, so that covers just about everything. If we were to go through a similar activity, looking at the equation of motion of a particle relative to the Earth, but we cancel that buoyant force so that we have gravity to worry about. We could solve this differential equation. So here, x, y, and z, these are relative to the Earth. So if we have a particle subjected just to gravity, and we measure its coordinates relative to the Earth, we get these equations that govern the motion of those particles. So similar to what we did, the mass cancels out. And you can actually solve these. So this is all covered in Commerce Notes. But you can actually solve these equations. Here's a simplification where we've neglected some small terms. The radius of the Earth, the angular velocity of the Earth is pretty small. So omega e squared will be much smaller than omega e. So these end up being the dominant terms. And this simplifies the equations quite a bit, to the point that you actually can solve these equations. And you can solve for x, y, and z as a function of the initial velocities in the various directions. And so this analysis then is applicable to, say, firing a bullet out of a gun. And if you fire over a long enough distance, we'll need to account for the fact that the particle is moving, and account for the fact that the Earth is rotating underneath us. So we have a fun little problem for you in the homework, where you'll calculate the trajectory that you would need to use if you wanted to throw a football from Lambeau Field to Chicago, Illinois, and calculate how you'd have to adjust the trajectory of the football to be able to make it, to make that long distance. All of this neglects air drag, which is actually usually going to be pretty important for anything moving in the air. So this is just something you could do to get a rough guess, but it does give you an idea of what those effects are. So here's an example. If we have a particle that starts at the origin of at the equator with lambda equals 0, and we have initially we fire it perfectly north and also up by 300 or 3,000 feet per second. You could plug these in and look at the numbers, and you can actually see how much the particle will drift to the west. I believe it's west. We'd actually have to look. Or actually, if we're at the equator, yeah, then it'll actually drift east, it turns out. So anyway, you can solve problems with this. I won't say any more about it because the derivation is almost the same as what we just covered, and these notes on the course website will describe that really well. Okay, so that concludes our lesson for today. We'll see you next time.